Hi, good morning. Welcome to AWS Research Seminar Series or Webinar Series. Today, it's really a pleasure to welcome Alan Parker. He's the Director of Natural Language Understanding in Amazon Alexa. The topic is really timely. Natural language processing or understanding is going into a huge phase of transition. It has been taken decades for scientists to understand human natural speech. And today, voice-activated artificial intelligence interfaces like Alexa and the processing system created by Amazon can interact with humans at various levels. In this webinar, we'll learn a little bit more about the internals of data flow within Alexa in response to a given spoken command and how natural language understanding stacks words and our investment in long-term deep learning and automatic model updates. About Alan, he's a world-renowned scientist. He joined Amazon in March 2018 as the director of engineering for Alexa NLU interpretation team. This is the team which builds core platform and technology as well as model that is used by both internal and external users. Alan has more than 20 years of experience in building and machine learning systems at scale, in security, in speech, in search, as well as in natural language understanding. Prior to joining Amazon, he worked at Facebook, managing various horizontal ranking teams, as well as before that, he was in Microsoft until 2014. More recently, he also led the Cortina backend technology team with Bing. With that, let me introduce, let me give it to the speaker, Alan. Alan, it's all yours.
Great, thank you, Sanjay. Thank you everybody for coming and listening today. As Sanjay mentioned, I lead a team in Amazon called, within Alexa called NLU Interpretations. And I've been building these kinds of systems for a long time now. It is frankly an overstatement. Thank you, Sanjay, for calling me a world-class scientist. I'm really not. I'm an engineer, but I've been building these kind of systems for a long time. My talk today is going to focus more on the use of these NLU technologies and some of the scale challenges that we're facing, rather than diving into details on the algorithms or the implementations. And so today we are going to talk about, I'm going to give you an overview of how spoken language understanding works in Alexa. We'll dive into the core NLU system and the technologies that we're using. We're going to talk about entity resolution, which is a related and kind of interesting problem. And then I'm going to talk about a little bit more forward-looking, some of the scale challenges we're facing, our transition from old-style linear models to deep learning, and some of the challenges around scaling across lots of different locales and building a global product. And hopefully we'll have plenty of time left at the end to do questions and answers. So let me start with an end-to-end overview. This diagram at the top of the slide is basically the data flow of an utterance through Alexa. So if you think about an Amazon Echo device, you've got a tube sitting on your desk or in your kitchen. And on that device, there's a set of array microphones and a simple custom silicon that's really just listening for you to say Alexa or the wake word. As soon as it hears that, it opens up a connection to the Amazon cloud and starts streaming your audio. The first thing it runs is the speech recognition. We call it ASR, automatic speech recognition. And that's taking the sounds that you're making and turning them into text. And that text in the sort of simplest implementation is just the one best, the thing that we think is most likely. What we're actually producing is a lattice of the alternatives sort of ranked in priority order. And so here we have an example of somebody asking for a relatively obscure song, Two Steps Behind by the band Def Leppard. And notice the spelling of Def Leppard. We'll talk about that in a future slide. The thing that runs next is my team's technology, the natural language understanding. And so we take that text and we're trying to turn it into fundamentally an understanding of your intent. So what is it that you're asking about or want to accomplish? And so the intent also comes with a set of what we call slots, basically the information we'd need to be able to complete your request or your action. So in this example, the intent is I want to play music, and the slots are the artist, Def Leppard, and the song title, Two Steps Behind. From there, the NLU system spits out a set of also ranked alternatives with the most likely interpretation at the top. And we have a series of rankers and dialogue manager that decides what to do with that information. And so in this case, where the request is fairly simple, it's a pretty commonplace one, and the action is easily understandable, we'll just hand it off downstream to what we call a speechlet, which is the thing that can render the answer and do the task that you've assigned. So the speechlet would use text to speech to take an answer like playing Two Steps Behind by Def Leppard, and actually playing that over your echo, and then call a music provider to actually play the song. Quite often, the task or the utterance, the intent of the user is incomplete, and we need to ask for either clarification or more information. So if you say, maybe we didn't understand the band name quite, so we might return back and say, which artist did you want? If you're asking for something like, Alexa, ask Uber to get me a car, we might actually say, great, where do you want to go? Or something like that to advance the dialogue to be able to fill the slots and make the action that you're asking for. So that's the end-to-end overview. And we're going to dive into some details around NLU, but first I want to do a little bit of a sidebar. The flow of an utterance through Alexa, that data flow, is remarkably similar to the flow of a query through a search engine, and that's not an accident. Most of the people who are in this business have spent some time working on search engines. I worked on both Facebook search engine and on Bing. And through a search engine, the input is a query, which is a short string that looks a lot like an utterance. And increasingly for search engines, that also starts with a voice search that goes through a speech recognition system and spits out a lattice or an n-best there as well. Query understanding is basically the NLU system, or one of the NLU systems in a search engine, where people a whole bunch of classifiers, machine learning models, and rankers run to figure out what is your intent. So in a search engine, are you asking for information like what's the fastest animal in the world? Are you asking for a weather forecast? Are you asking for local search and some destination, a place in the world? That list of likely intents are then used to go do a bunch of lookups, and this is where search engines really have to scale to go look up against millions or potentially billions of potential web results. And then a system of rankers, again, that will figure out what are the most likely and best answers. And then in a search engine, their rendering instead of speech is what we call a search engine results page. It's HTML with the most likely answer somewhere near the top, page search results, web links, other answers. And one key difference on a search engine is that they get to render multiple answers. So it's again important to have the answer at the top. So if you ask, what was the Seahawks score last night? Most search engines will just give you the answer, but then there'll be links to the Seahawks webpage and fan sites and things like that. And one of the key advantages there is that the click stream, what the user does in response to that, the rendering of the results, is a really strong signal for a search engine. They can use what you clicked on to think, oh, that was the best answer for this person. And for Alexa and assistants that especially run on headless devices, things that don't have screens, we really don't get that signal in any strong way. So if you ask for Alexa, what's the weather tomorrow? And we recite out the answer for you, and then you walk away. It's actually really hard for us to know, did we get it right? Did we satisfy you? Did we make you happy as a customer? And so we'll talk more about that coming up, how we pick up other signals to understand whether we're doing a good job in satisfying our customers. All right, let's dive into the NLU technology. So this, first of all, is a wildly simplified view, but it captures the major concepts. We have a set of statistical models that run anytime you speak to an Alexa device. And they run conceptually mostly in parallel to get ranked at the end to come up with the most likely interpretation. So the first concept is named entity recognition. So these are really the slots that we think will be important to be able to answer your question or fulfill your intent. And the named entity recognition, a lot of what we're doing is just trying to recognize something that might be important. So there we tune for recall, just don't miss things. We also have an intent classifier or a set of intent classifiers. Within Alexa, we have hundreds of intents, and I'll talk more about that coming up, but trying to figure out, are you asking for a weather forecast? Are you asking us to play a song? Are you asking us to turn the lights on? In parallel, we're also running a set of domain classifiers. So are you asking about weather, music, sports, smart home automation? And the reason that that runs in parallel is that there's a bunch of shared intents. So the concept of, say, play is something that spans across games, music, videos. And so we're trying to understand both intent and domain. And then all of that feeds into a set of rankers and what we call entity resolution, where we're trying to take these named entities and resolve them to an authoritative provider that knows something about that entity and can do something actionable with it. And I'm going to dive into each of these in upcoming slides. But if you look at the example in the lower right, the utterance the user said was play songs by CCR. NER, named entity recognition, said CCR is a musical artist. The domain classifier said, we're pretty sure this is music because you said play songs. The intent classifier said this is most likely a play music intent because Creedence Clearwater Revival didn't do much except make songs. And then entity resolution can resolve that to Creedence Clearwater Revival, the actual canonical name of the band, and a whole bunch of meta information about providers for their music, biographies, etc. Lots of information that we have about CCR. Okay, so next, let's talk about intent classification. So in the last slide I mentioned there are hundreds of different intents that Alexa knows about natively, and we've announced publicly that there's tens, I think we've even said that over 100,000 third-party skills, people who built skills using the Alexa skills kit. And so the number of intents that people might ask about are very, very broad. And so that creates a classification problem in and of itself. And then the language that people use across each of these intents is more or less unbounded. So here's a simple example of people wanting a weather forecast. And if they ask what's the weather or tell me the forecast, that's pretty easy to figure out and pretty easy to both collect the data and train a model to be able to service that intent. If you look at the end of the list, you're getting into some pretty obscure examples like, do I need an umbrella, or what's the expected low temperature? And it turns out learning that language like that, an utterance like that, is associated with a weather forecast intent is a harder problem to do, particularly in an automated or scalable way. So think about this problem times thousands of different intents times dozens of different languages, and you start to get an idea of the scale challenges that we're facing. Next, named entity recognition. So I mentioned earlier that here we're going for recall. We basically don't want to miss anything that might be important. And this is another largely unbounded problem. So we're going to talk about just being able to understand that you're talking about a date, but in named entity recognition can span almost anything that humans can think of. So it might be an artist like Pink. It might be a person like Alan. It might be a thing that you've named in your house, like the family room lights. And so these things can be both very broad and very personal. And again, the language that people use to describe them can be very non-deterministic. So looking at this example of a date, March 27th, that's a fairly standard way to talk about a date, but people might say 3/27, or they might say the 27th. And all of those have to be recognized correctly as a date. And then when you get into these sort of indirect references, like 2 days after Good Friday, not only do we have to recognize that as a date, but later we're going to have to resolve that to something structured and actionable. And I'll talk about that when we get to entity resolution. Okay, now we get to the really interesting problems. Across those hundreds and even thousands of intents, when you consider the external skills, given that some of these intents are shared anyway, resolving ambiguity across all the different ways humans can ask for things turns out to be a really hard and really interesting problem. And so in addition to these individual models that are trying to say, I think this person's asking about a weather forecast, or this person's asking to play a song, we then have to rank across the domains to figure out what's the most likely answer. And because we've got all of these systems of models, each one of them has its own sort of confidence or error rate, and when you sum them up, the error rates can get pretty high. And so what we're trying to do is pick the most likely interpretation across all of these different models and possibilities. And so here there's an example of the user said play Frozen. And that's a pretty simple one, but it ends up being there are some cases, edge cases, that are pretty difficult. The ASR hypothesis in this case, and by the way, this case is made up, it does happen in real life, but the values here are just for illustration. The ASR speech recognition was pretty sure that you said play Frozen, but it also thought you might have said play songs. And so that goes into our re-ranker. We came up with different possibilities around your intent. Pretty confident that you mean play music. Also somewhat likely, pretty likely that you wanted to play a video. And then if you look at the F1 through F4 on the right side of the table, those are a set of features that that we use to rank against. And these features are can be contextual, they can be personal. And so if you look at F3 and M4, those are personalized signals, like have you bought Frozen, either the song or the movie. F4 is about your past behavior. When you asked for Frozen before, did you want a video or a song? And that is sort of a real world case. The most common one is Baby Shark. People who ask for Baby Shark ask for it over and over and over again. And so if you look at feature 1, devices connected to a screen, in this case, that's a really strong and important signal, because for Frozen or Baby Shark, if you're talking to your Fire TV Cube or you're talking to your Alexa show, you almost certainly want the video. If you're talking to an Echo, you know, the tube without a screen, it's very likely that you want the song instead. And so all of those get ranked up. And in fact, in early versions of this ranker, we really did just sum these up and score them. Now we're using more sophisticated deep learning approaches to learn the relative weights of these features in the context of each other. But the concept is actually pretty simple. And so in this example of play Frozen, there it was relatively easy to resolve because you know, your past history and whether you're talking to a thing with a screen end up being the strong signals. But we run into much more complex obstacles, and one that we were having a kind of a deep dive and a debate on recently was the utterance, Alexa, remember to feed the baby at 2 p.m. Now, that's a pretty obscure utterance. It turns out across the billion utterances a week, people talking to their Alexa devices, that happens 50 to 100 times a month. Somebody will say, Alexa, remember to feed the baby at 2 p.m. And it's you know, it's not a common thing, but it turned out we had a bunch of different domains and intents that said, I can handle that. So the reminders team thought they should handle it. The remember this team thought they should handle it. The calendar skill felt like they could handle that. And then the health team thought that they could handle it as well. In fact, the answer is they can all handle it. They could probably all render a reasonable answer for the user. But how do you pick? And this is where we use the ranker. And in fact, the answer is likely to be different for different users. Some people actually wanted to set a calendar appointment. Some people wanted a reminder at 2 p.m. for their device to speak up. Some people wanted to actually collect that in the health skill and build a tracker over time of when they're feeding the baby. And so all of these signals get used to make a personalized, contextual, runtime decision about who gets to answer. So that's cross-domain ranking. All right, let's talk about some of the challenges that we're facing with these systems. So the first one is that we talked about this, that across these different utterances, there are lots of different potential intents, and we need to use other signals to decide when you say play Frozen, which really doesn't have very much information, what's the most likely interpretation for you? Next. Entity recognition turns out to be a really hard problem, not just because of the language that people use, but because when people are using spoken language, the ability to recognize which entity you're talking about. And in fact, these words tend to have lots and lots of overlap. So it turns out Dead Mouse is both an artist and there's an album, and there's probably a song called Dead Mouse as well. Speech recognition is still quite inexact, particularly, Alexa does far field recognition where people are talking to a device that could be 10, 15, 20 feet away. And in a noisy environment with the TV going or music playing. And so quite often the speech recognition will spit out something that is not ridiculous, but not the right answer. So here's an example of an Indian artist, Dev Anand. The speech recognition thought you said play David and music. And so the NLU system has the potential ability to recover from those kind of errors. And then finally, there's what we call out-of-domain utterances. Again, you have a device in your house with that's listening for you to say Alexa. We really do struggle in households where people are named Alex. In my house, which is full of Alexa devices, it turns out I say Alexa a lot. And so one of the things that we're doing is trying to figure out, are you actually talking to Alexa? And so we have signals like whether the user is facing any of the microphones on the Alexa device. So device directedness is a pretty strong signal for us to be able to reject something if you're not talking to us. We'll also just look at it like if it appears that it's not any of the domains or intents that we know about, we can reject that as well. And so, so these are just some of the challenges that we face around NLU. These are kind of the core technical issues. I'm going to talk about some of the scale challenges coming up as well. All right, next let's talk about entity resolution. So I talked earlier about named entity recognition, and there we're trying to find people mentioning entities, again, with the belief that we might need that to fill a slot and complete a task or answer a question for you. Resolution is about trying to resolve that entity to some canonicalized version, a structured representation that we can take action on. So Kesha is a musical artist. She represents the S in her name with a $. Being able to recognize that and then connect that to some canonicalized value linked to the various catalogs from Amazon Music, Spotify, Pandora, Wikipedia, all the information and actions that we can take based on that artist. Sometimes you want to canonicalize to a more standard representation. So LA, which the speech recognizer will recognize that you're saying the letters L and A, but the entity resolution system needs to understand that you're talking about the city of Los Angeles. And then earlier we talked about dates. If somebody says tomorrow, not only do we need to recognize that's a date, but we want to turn that into a structured representation of the actual date that we can use to complete whatever intent or task you've assigned to us. So challenges around entity resolution. So the first one is, particularly in the music industry, the written form of these entities often looks nothing like what the words sound like. So Dead Mouse is a DJ and spells the S with a 5, and so humans get this pretty intuitively. if you can sort of teach your machine learning models and provide the data to resolve that, great. But learning this in an automated way is where, and across all of the entities, all the domains, all of the languages, this gets to be a real hard problem. There's lots of ambiguity in the way that people refer to entities. And so here's an example of Taylor Swift has a song called I Knew You Were Trouble. Most people just ask for Play Trouble by Taylor Swift. And so the word trouble, of course, is pretty common in the English language. So being able to resolve to that entity, you do have a strong signal because they said by Taylor Swift. But also there's a statistical component to this, that if people play trouble, they're most likely to mean this song. And so those are things that we can learn over time as well. So we talked earlier about Frozen, but play the Frozen soundtrack. At that point, because you said soundtrack, we can be fairly confident that you're talking about that you want to hear music. But within Alexa, there's a bunch of different music providers. And so how do we decide whether you want Amazon Music, whether you want Spotify, whether you want Pandora? And these are things that can get ranked based on personalized or contextual signals. So if you always use Spotify, over time, we'll learn to play it on Spotify. Oops, sorry, go back. And then finally, scaling this across all of the languages becomes really hard. And in particular, because the entities themselves tend to not be multilingual. So the song Trouble by Taylor Swift, people in India or Mexico, they all want to listen to that song as well. And so we've got these sort of language switching problems and being able to canonicalize and recognize across all of the different catalogs that might be talking about a given entity. So those are some of the entity resolution challenges we're facing. Let's talk about scale. So the first one, earlier I showed you a diagram of the different types of statistical models, named entity recognition, intent classification, domain classifiers, re-rankers. That's only part of the picture. And in fact, every one of these systems that runs at scale, whether it's a search engine or an AI assistant, relies actually pretty heavily on rules for a couple reasons. The first one is that rules behave deterministically. So if you write a rule that says, if somebody says, Alexa, what's the weather? Show them a weather forecast. It behaves that way forever, as long as that rule exists. And you don't have to worry about model retrains changing the behavior of the system. The other thing is that rules are a lot faster to write than collecting data and training statistical models. And so for that reason, people tend to prefer rules intuitively because they behave in more predictable ways. However, they're brittle and they don't generalize. And so you can write a rule that says, that can answer Alexa, what's the weather? But that won't handle Alexa, what's the weather tomorrow? Or Alexa, is the weather going to be nice? And so this is why you need statistical models for the tail. And so what we try to do is balance when to write a rule and when to generalize with statistical models. And there's a couple of guidelines that we use. The first one is you need rules for bootstrapping. If you're trying to build something new, you sort of have to collect the data and write the rules before you can get to the point where you have enough data to build statistical models. The other thing is we try to memorize the head. So if somebody asks, Alexa, who's the president of the United States? Or Alexa, play music, we should never get that wrong. And so that's an appropriate use of writing a rule. But if somebody's asking something obscure like, Alexa, remember to feed the baby at 2 p.m., that's the kind of thing that trying to anticipate that and write a rule in advance just doesn't make any sense, and it really does not scale. So that's where we apply statistical models. Second scale issue, getting ground truth, either for rules or for statistical models, is increasingly expensive. So having to, any place where you introduce humans into the system, that is a place where we struggle with scale. And so I mentioned earlier, we've got thousands of intents and dozens of locales. That in itself turns into a really difficult scale problem. And it isn't just about either writing rules or collecting data for training models. Our ability to measure our accuracy and test these models and test the performance of the system gets really difficult. So I mentioned earlier, there's 100,000 third-party skills. Many of them are written by hobbyist developers, and they're relatively low traffic. How do we understand whether the system is performing well on those and whether those skills are effective for the customers that are using them? You simply can't use humans to measure accuracy at that scale. And so we're working on a bunch of different automated ways, largely based on people's behavior, to try and figure out whether they're satisfied with what we've done. And so as an example, if people ask for something and then rephrase it slightly, that's a pretty good indication that you got it wrong the first time and that you might have gotten it right the second time. And so search uses this as well. They call it query rewriting. And so if people retype queries and then click on something, that's a strong signal. We can use similar kinds of things here. It turns out if people get frustrated and you can detect sort of emotional levels of interaction, those are also signals that we can use in automated ways. And so behavior signals become increasingly important for us. And then a scale challenge we're in the middle of right now is the whole industry is changing to deep learning. It turns out DNNs are really expensive. And so you have to apply them in sort of careful ways. And pretty much everyone in the industry is in the middle of this transition where you have to figure out when you can use bigger, more complex models, when you can afford to pay the cost of increased latency and increased cost to be able to both to train the models and at runtime. And so there was press recently about the cost of training some of these big DNN models at other companies uses the energy equivalent of building a small car. I don't actually know if that's true, but these things are extremely intensive in terms of compute and memory and the power consumed. And so, and that's true both when we're training the models and evaluating the models and deciding whether to put them into production, and at runtime as well. The inferencing, the ability to decode at runtime is much more expensive than rules or linear models. And so I'll talk about that, some of that coming up as well. Okay, so deep learning at this point, it's certainly not new, but it really has been a revolution in AI. It's provided this sort of step function improvement in accuracy, and it's where all of the future advances, it's all the research in both academia and industry is happening. And so switching to DNNs, we see this improvement in accuracy. What we've seen is across the board, we get about a 10% decrease in the error rate for NLU. And that isn't even really the whole picture, because on the head where it's easier to get the play music right, we're not seeing much gain. And so the gains are all coming on the tail. They're coming in places where we don't have much training data, where they're low resource domains or languages. And so it's really helpful for the things that are harder to do with rules or linear models. And one of the things we find is that they're not necessarily better the day you turn them on. These things need data, they need tuning, and so you end up having to basically take the leap and then tune, and you can see very, very large gains in accuracy. So accuracy is one really important piece of it, But it also, in the case of the scale that we're running at, it's almost more important that DNNs are the things that enable automation and removing humans from the loop. So DNNs work really well with unsupervised and semi-supervised learning. You can take just raw data, run a collection of models, and if they all agree, that's a good indicator. Semi-supervised learning, we can take advantage of behavior signals like retries and other signals based on what users actually do in response. So like if people are shopping and they buy something, that's a signal. If they're shopping and they don't buy, that's a weak signal because they might just be going somewhere else to buy, or they're going to buy later. All of those things are things that DNNs can learn. We're also using DNNs in an offline way to do active learning and selection of data that we're either going to submit to humans to take a look at, or that we're going to use for training and testing. I mentioned earlier that few-shot learning, so in languages where we just don't have much data, Italian, for example, DNNs can get up to speed with a lot less data and get you to the point where you can put something into beta and start collecting data at scale. DNNs are also useful for transfer learning and machine translation, and I'm going to dive into those. I got some slides coming up on that. So transfer learning is almost magical. What we find is that the hidden layers of these deep neural networks, we do sort of feature transforms on the text, the embeddings that are generated for the n-grams and the tokens in the utterance, actually end up encoding the semantic meaning of the utterance. And not in a way that humans can understand. These are just basically vectors measuring things like distance to edit distance across other utterances. But they can carry around the concept of something like reservation. And that works both from domain to domain. So we can learn the concept of reservation from restaurants to hotels. And it also works across languages as well. So the concept of reservations translates from English to German. And so we've been able to bootstrap both new domains and new languages much more quickly. So this is, again, a pretty high-level picture, but if you're starting with one domain that has plenty of data, so music, for example, shopping, the idea that you want to buy something, those embeddings that come out of the models that we build in the mature domains can be used for a new domain like traffic. And this is an interesting example. If you see the source domains where we have weather, music, and shopping, doesn't look inherently like there's a lot of overlap with a traffic domain. And that's because it doesn't have to be something that's intuitive to humans, like making a reservation. The semantic representation of just the language that humans use transfers from domain to domain. So a related concept is pre-training. So using these embeddings and reusing them. I mentioned earlier that training these big models is expensive, and there was press around as much energy as building a small car for one of the other companies in this space. And so it turns out you don't have to regenerate these embeddings every time you train. So we use a technique that we call pre-training, where we can basically carry these embeddings and this knowledge around to different domains. And so the training for the next domain can be what we call fine-tuning, where we're just adapting to the new target domain. And this works not only from domain to domain, it turns out it's really efficient for within a domain. So we've got very large models for things like music, for example, where it's a relatively complex space and a really complex set of catalogs of songs and artists and things that people want to do with music. And it turns out the core intents around music, like play a song, really don't change very often. And so we can pre-train base models within the domain, say once a month, and just fine tune with, say, new catalogs, new songs that have been released today, and adapt the models to be able to handle those. And this ends up being much more efficient. We see virtually no degradation in accuracy over the course of a month. But we're able to update and pick up new songs as soon as they come out. And so it's a really valuable efficiency and accuracy technique for us. Okay, last section, let's talk about scaling into other languages. Alexa is a global product. We support a dozen locales now, and that's growing all the time. When we want to enter a new locale, German, Italian, Indian, the Hindi, there's a bootstrapping problem, and then there's a data collection problem as we start to ramp up a new locale. And so when you start, we collect what we call golden utterances, which are samples of how you would say, play a song or turn on the lights. We build grammars that can generate a bunch of variations on those. And we do sort of manual in-house data collections with, for example, our own employees. And there you really are able to collect hundreds or perhaps thousands of utterances. You have to get to a certain level of accuracy to even be able to use this as a beta. When we get to that point, we can turn it on and start collecting data at bigger scale. But again, the ability to have a human look at that data and turn it into something useful is difficult, and it's even more difficult in other countries around the world. And so DNNs help with this. We use techniques like transfer learning and machine translation to be able to generate more data where we don't need humans to be in the loop. And so in the early bootstrapping phases, we've had pretty big success with machine translation, where we can take the English training utterances, the training and test data, and translate those in various ways, and I'll dive into those in upcoming slides. And then later, when we're starting to collect a bunch of data, but we don't really know what people are saying in other languages, we can use a technique called cross-lingual annotation to be able to build more training and test data to improve the accuracy in that new locale. So the simplest version is just translate the full sentence. So if you've got a training or test utterance like play music by Katy Perry, we can translate that from English into German and just use the German version of that utterance to train a German language model. This actually works reasonably effectively, but you have a couple of technical issues here. The first one is you are limited by the accuracy of your machine translation models. And one of the things that we've run into is the utterances, the language that people use when they're talking to Alexa really is different from the language that people use when they're talking to other people or writing documents or using the web. And so existing machine translation models have limited accuracy. We've started to build MT models that use Alexa utterances to improve the accuracy there. But still, there will always be some level of inaccuracy. The other problem we have is around the annotations, being able to recognize the parts of speech or the slots or the intents. Different languages put just order their sentences differently. And so we lose some accuracy there around the annotation. And so we can do this same machine translation technique at the feature, token, or n-gram level. So what we can do is just look at the n-grams, the combination of words within an utterance, and translate those as well. And then carry around the embeddings from the English language, the weights of those features, and use those in German. So that's doing that at a lower level of granularity. And we find that we actually get better accuracy with this technique. In fact, we use both because they both bring different sort of levels of coverage. But this is a variation that helped improve our accuracy. Then once we're running, we can use cross-lingual annotation. So we take the non-English utterances that we're collecting from our utterance stream, like I don't speak in German, so I'm not going to say this, but play music by Katy Perry in German. We can translate that into English the and then project the annotation of the English version onto German, and then train and build a German language model. And this can be done both at runtime and offline. So you can build a system that can do this basically in real time when users are talking to it. We've had less success with that, frankly, both for latency and for accuracy reasons. But this also works offline, and it's where we've had more success with being able to just generate more native language training data for these new locales that we're trying to get up to speed and improve the accuracy in. So that is it. That is the end of my deck, and we are, I think, ready to take questions now.
Thank you so much, Alan, for the talk. From the audience side, please post your questions in the chat. I'll take it from the chat window. So by the way, while we're getting questions, I just want to announce that this webinar will be available here and in our YouTube page. We also record all the past webinars in our research seminar or webinar series. The next one, we plan to talk about frontiers of science using petascale computing. This is how we are pushing boundaries in scientific studies using large-scale computing infrastructure. That'll be on November 13th. Please do register. It will be available very soon on this particular page. Do we have any questions? There seems to be a question. I cannot see it.
Perhaps I can help. Sorry, there is a few questions here. When you have a few possible resolutions of your user intent with similar probabilities, do you ever ask the user to choose between most likely intents? This was a question from Scott.
Yeah, absolutely. So in that first workflow slide, I talked about a clarification dialogue. Ambiguity can sort of surface in a bunch of different places in the system, either out of the speech recognition or the NLU interpretations. And yeah, we do have what we call a disambiguation dialogue. And sometimes we'll say, I'm sorry, I didn't catch that, or we'll say, did you mean this or this? And we use that somewhat sparingly. We find that people will tolerate it occasionally. If you do it too much, it tends to drive down engagement and people talk to their Alexa devices less often. But yeah, disambiguation and just asking the user for feedback is definitely an important tool. And by the way, it's also a really good reusable signal for whether our hypothesis was right, and that turns into training or test data that we can use to improve the models later.
All right, I have another question. Thank you, Scott, for asking that one and getting the answer to Scott. I appreciate that, Alan. So another comment from Terry. Thank you, Alan. Can you say a little more about the testing of the cross-national translation process you build? Does it involve humans?
So yeah, almost all of these systems involve humans because fundamentally at some level, you still need some level of ground truth, and you need the ability to bootstrap these languages. Our goal is to reduce the amount of human intervention that we need. So as an example, in there I was talking about English to German. So our current German production models, we were able to reduce the amount of human annotated data necessary by 50% over the previous version, the linear model-based version. And so, I don't think we ever get to a point where there are sort of no humans involved in the system, at least to start. But we do believe we can get to a point where the system improves in an automated way, and humans just have to review occasionally. And so our goal is automation at scale. but you still fundamentally need some notion of ground truth.
So the next question is from Jana. It's, may I ask you about the scope of machine learning algorithms in NLU?
I'm not sure I understand the question by scope of machine learning algorithms, but let me take a shot at it. So I guess first of all, the first generation of these ML algorithms were linear models, where in our case we were using maximum entropy as for our binary classifiers like domain and intent classifiers, and CRFs to conditional random fields to fill the slots. We are in the middle of transitioning to deep learning, largely based on sort of where we need it and can afford the cost in terms of latency and compute. And we're experimenting with literally dozens of different algorithms. So one example of one that is working pretty well for us is bidirectional LSTMs. One of the things that we've done is both with our offline model training and our runtime is we've built a flexible framework that lets us experiment with lots of different algorithms, both offline and in production. And it's pretty clear there will be no one size fits all. We'll probably do varying levels of complexity based on sort of domain and locality. I hope that answered the question.
Okay, we'll get a comment from Jana on that. In the meanwhile, I'll ask you another question, Alan. This one's from German, and this one is, please tell us about automatic equivalence class learning.
This is where you're hitting the limits of my knowledge. We have been experimenting with it, but I honestly don't have much knowledge about what we're doing and how well it's working.
Okay, no worries. There's a question from Ree. Is there a development framework or interface available?
So yes, so the external developer framework is the Alexa Skills Kit. And so ASK, as we call it, like I mentioned, there's over 100,000 skills that have been built using that. Today, there's a trade-off that we're making around simplicity versus power and flexibility. And right now, the Alexa Skills Kit is biased more towards simplicity. So it's a great developer experience and sort of user interface where you just define your intents and slots, bring simple catalogs, and a small number of sample utterances. And then we used a bunch of synthetic data generation techniques to generate a fairly large training and test set. And develop a model for you that in a really automated fashion. But because of that simplicity, under the hood, we are starting, there's again a mixture of linear models and neural networks. But you get very little sort of ability to tune that, to decide sort of what level of complexity you want. And that's sort of what's on our roadmap moving forward. But if you haven't played with the Alexa Skills Kit, definitely recommend it. It's actually a really nice interface in terms of, you can get a skill up and running within an hour or two. And then there are actually fairly large, sophisticated skills like Jeopardy, Domino's Pizza, Uber and Lyft. You can do fairly complex interactions and complex tasks that were built using that simple developer interface.
Great. Can you say a little more about the testing of the cross-national translation process you build? Does it involve, I think we did this one, does it involve humans? Did you do this question already?
Yeah, I did, yeah.
Okay. Let's see, are GANs used to generate training data? GANs. I don't know what that stands for, unfortunately.
Yeah, I actually do not recognize the term either.
I think what he means is generative adversarial network are used to generate the data.
So in some cases, we are experimenting with adversarial networks, but it isn't in wide production use for us yet.
Okay. Let me keep going then. Is dependency parsing enough for avoiding ambiguity in the meaning of the tokens?
So Probably not. In fact, we're mostly not doing much in the way of semantic parsing. The thing that scales and works well is more around generating these embeddings and letting a neural network learn the dependencies or the relationships of these tokens.
Okay, this one can go to both Sanjay and you. So both of you could attempt to answer this one kindly. Will you describe the compute infrastructure you use to stand up the NLU service? So one could be what we're doing for Alexa, and perhaps Sanjay, from a researcher's perspective, you could guide the team, the participants on this one. Yeah, go ahead. Your shot first, Al. Your turn first. Yeah.
Sorry, did you want me to go first?
Yeah, you go first, and then we'll have Sanjay comment on this one from a research perspective.
Yeah. Okay. Well, so first of all, hopefully it is not a surprise to anybody that we use Amazon Web Services as our compute infrastructure. There's both an offline sort of training and evaluation component where we are generating, at peak times, like around the holidays, billions of adapted models per day, because we have a whole bunch of personalized models for users. And so it's largely about horizontal scale and elasticity to hit the peaks. At runtime, we have similar concerns, but there the latency becomes much more important. And so we built a system that we tend to provision for peaks, and we have a latency goal of basically returning an answer in less than a second, and that leaves in the neighborhood of 50 milliseconds budget for the NLU models.
From a researcher's perspective, could you answer that kindly, Sanjay, and then maybe you can wrap up, because we have more questions, but we can't get to them given the time. So answer that question for us, and then maybe you can close out the webinar as well.
Yeah, absolutely. Thanks, Naida. Yes, people do use from researcher perspective all the computing and other infrastructure we have. For example, for large-scale AI machine learning, people do use the GPU-based infrastructure, but also sometimes people do deep learning training on GPUs. We call it Amazon P3 instance. But inference sometimes on FPGAs. So this is one of the studies we are doing with high energy physics, where we are trying to do training on GPUs, but to accelerate time to science, we sometimes use FPGAs for inference. So we do provide work on several infrastructure using AWS. I welcome everyone to try it out for their studies, and let us know if you need any help. In terms of next seminar series, it's really fascinating. The next one, as I said, is touching base on frontiers of science using petascale computing. So as we see computing, even from Alan's talk and other talks, you can see computing is going into an era of heterogeneity in resources, right? In the past, they used to be like supercomputers, which is homogeneity in resources. So next seminar series will touch base what are the modern sciences we do both in high throughput and HPC that kind of pushes the boundary of heterogeneity in computing in using AWS and elsewhere. We'll have a speaker from one of the fastest supercomputer in the country. It's called Frontera. NSF just funded it. He'll talk about how he's pushing the boundaries of science with Frontera, but also using cloud. And we'll discuss a lot more details along those lines and what are the different domains we can touch and all. So I look forward to seeing you guys on November 13th at exactly this time. Thank you so much for coming. This will be recorded and will be available in YouTube. Thanks a lot.